Chapter 5 on Cheng 10th edition on the gases. First off, a few properties of gases. They assume the volume and the shape of their container, unlike solids and liquids, although liquids will assume the shape of their container. And they can be compressed. Now, technically all states of matter can be compressed, but gases can be compressed a lot. They mix evenly throughout their container, so they'll fill the volume that they are occupied within. They have very low densities. That's why things float usually. And then they supply a pressure. Pressure is defined as a force applied per unit area. And pressure is one of the main topics that goes over in the gases unit. Last thing to mention with pressure is there's some very common units. A Pascal, although we'll talk about a kilopascal, millimeters of mercury, atmosphere, and not as used as often as the PSI, which is pounds per square inch. Conversions to know with these different pressures is that there's 760 millimeters of mercury in 1 atmosphere. This is also referred to as sea level. The pressure at sea level is that 1 atmosphere. 1 atmosphere can be related to kilopascals as well, 1.325. And again, pressure is usually measured in an instrument called a manometer. There's a few basic gas laws that you need to be aware of. First off is Boyle's law, which is the inverse relationship between pressure and volume, which means that the pressure increases on a gas, the volume will decrease. Charles' law is the direct relationship between temperature and volume. So in other words, if you increase the temperature of a gas, the volume that it occupies will increase. Gay-Lussac's law is the direct relationship between temperature and pressure. So once again, if you increase the temperature, the pressure of the gas will increase as well. All these gas laws are here on the board. So you can see Boyle's law is the first one, P1V1 equals P2V2. Charles' law is V1 over T1 equals V2 over T2. Gay-Lussac's law is P1 over T1 equals P2 over T2. Now the last thing I have on this slide is we can actually combine all of these gas laws together to form what's called the combined gas law, because they have the same variables within them. And once again, the 1 and the 2 represents the before and after situation. So the combined gas law is going to be P1V1 over T1 equals P2V2 over T2. Within the gas unit, absolute zero is mentioned as well. This is the theoretically lowest attainable temperature, which is called 0 Kelvin. So when I show you a T for the the combined gas law, or the Charles law, or the Gay-Lussac's law, this temperature is measured in the Kelvin scale, which again, 0 Kelvin would be the lowest possible temperature. The conversion you need to know is 273 plus the degrees Celsius. You might see it as 273.15 otherwise, but 273 plus degrees Celsius should work out just fine. Now, thermodynamics is when we'll discuss more about what does it mean to be at absolute zero. The ideal gas law is based off of Avogadro's law. Avogadro, you might remember from the 6.02 times 10 to the 23rd number. Avogadro's law states that at constant pressure and temperature, the volume of a gas is directly proportional to the number of moles. So in other words, it doesn't matter what type of gas it is, what the size of the gas molecule is. Every gas molecule at the same temperature and pressure will occupy the same volume. The equation here is PV equals nRT. Within PV and nRT, it is very unit specific. So first off, pressure has to be in atmospheres, volume has to be in liters, temperature has to be in Kelvin, N stands for the number of moles. Finally, R is the ideal gas law constant, 0.0821. Don't get confused when we talk about energy in later chapters. There's a different R value when dealing with joules of energy. Notice the units on the R value. They don't mean anything. All the units are there for is to cancel out the units within the rest of the equation. So you should always know then, okay, what do I need to have my units in to use this R value? Standard temperature and pressure is something that's often referred to as, within a chemistry problem, STP is what we might call it. The pressure would be 1 atmosphere. The temperature would be 273 Kelvin, which if you think about it, that's 0 degrees Celsius. So standard temperature really isn't a normal condition. Normal condition of 1 pressure, yes, but not temperature. Solve for the volume of 1 mole of any gas at standard temperature and pressure could be a problem we ask you to do. So if I show you this on the board, 1 mole is mentioned in the problem, so I know I'm using PV equals nRT. And once again, if you prefer to isolate the variable, because we want to solve for volume, volume would be nRT over P. From there, 1 mole of any gas, R value 0.0821. Standard temperature would be 273 Kelvin over standard pressure 1 atmosphere. any gas at standard temperature and pressure and only 1 mole would occupy a volume of 22.4 liters. We're going to do another problem on the board right now. The last question on this slide says a sample of oxygen gas initially at 0.97 atmospheres is cooled from 21 degrees Celsius to negative 68 degrees Celsius. What is the final pressure? You will notice that there's a temperature and a pressure involved in this question. So what I need to do, P1T1 equals P2T2. Again, if you want to isolate the variable, great. Otherwise, I'll show you this time just how to plug it in. Initial pressure is 0.97 atmospheres. Initial temperature says 21 degrees Celsius, but my temperature has to be in Kelvin. So I'd add 21 and 273. So this is actually 294 Kelvin down here. Same on the other side, P2 is what I'm solving for. Over T2, well, 273 minus 68 would be 205 Kelvin. If I solve for P2 now, I just have to multiply both sides by 205. 0.97 times 205 divided by 294 would get me an answer of 0.68 atmospheres. Which, once again, if the temperature decreased, which is what the problem says, it makes sense that the pressure would decrease as well because they're directly related. We're going to move on to the next slide where it's a combined gas law question. So the gas initially at 4 liters, 1.2 atmospheres and 66 degrees Celsius undergoes a change so that the final volume and temperature are 1.7 liters and 42 degrees Celsius. What is the final pressure? Again, I see liters, atmospheres, and temperature all within the problem, so that means I need to use the combined gas law. P1 V1 over T1 equals P2 V2 over T2. And it's your choice of either isolate the variable or just plug it in right away. If I plug in right away, I have 1.2 atmospheres is my pressure. My volume is 4 liters. Over my T1, which is 273 plus 66, that's 339 Kelvin, equals P2, what I'm trying to find, times V2, which is the 1.7 liters, divided by T2, 42 degrees plus 273, which is 315 Kelvin. If I multiply 1.2 times 4 and divide it by 339, I would then also have to multiply by 315 and divide by 1.7. My P2, when I calculate all this, would end up being 2.6 atmospheres. So again, a combined gas law problem, you'll see pressure, volume, and temperature involved. How you know when to use the ideal gas law is you'll see moles or even grams possibly involved, because we should know how to go from grams to moles at this point. Another application of this is in solving for density of a gas. Density, as we should hopefully know, is mass divided by volume. This can be substituted into the ideal gas law, though, to solve for something else. Although unlike solids and liquids, which usually density is measured in grams per milliliter, since gases are not very dense, its density unit is grams per liter. Question could be, what is the density of uranium hexafluoride at 779 millimeters of mercury and 62 degrees Celsius? Because density is dependent upon temperature. So the equation given to us for density is Pm over RT. P stands for pressure. Given to us in the problem, 779 millimeters of mercury. We will have to convert that to atmospheres, though. This M does not stand for mass. It stands for molar mass. So if the question asks for uranium hexafluoride, look on your periodic table, figure out what is the molar mass of uranium hexafluoride. That's the value that goes right there. R is still the ideal gas law constant. T is still the temperature. So if I plug all this in, first off, 779 millimeters of mercury is the same as 1.025 atmospheres. We have to be in the correct unit. The molar mass of uranium hexafluoride is 352.03 grams per mole. Divided by R, which is 0.0821. And then finally, my temperature of 273 plus 62 is 335. When I solve this, I get a density of 13.1 grams per liter. Which again, remember your unit is grams per liter. You can always look back at the R gas law units to figure that one out as well. So besides using density, we need to do the other version as well. The last problem on this slide says the density of a gas is 3.38 grams per liter at 40 degrees Celsius and 1.97 atmospheres. What is the molar mass? So the density equation I just gave you can be rearranged. Molar mass can equal dRT divided by P. So now we can solve this problem. So now we can identify what the gas is. The density in this case, once again, is 3.38. The R value is 0.0821. And then temperature is 273 plus 40, which is 313. Divide that all by the pressure, which is 1.97 atmospheres. And we get a molar mass in this problem to be 44 grams per mole. Now possibly it could be a multiple choice question where they then ask you which of the following is most likely to be that gas. I know carbon dioxide has a mass of 44 grams per mole, so it could be something like that. You might just have to identify it or just stop at that point. Either way, again, it's just a manipulation on the density equation which we plugged into from the ideal gas law. The next thing to bring up is stoichiometry in a gas problem. So we can use the ideal gas law within stoichiometry too. It says find the volume of carbon dioxide produced from 37 degrees Celsius in 1 atmosphere when 5.60 grams of glucose is metabolized. We need to use stoichiometry because we're given grams of glucose, but we want to solve for carbon dioxide. At the same time, stoichiometry only goes grams to grams. It doesn't involve volume. So we have to do a little bit of stoich, a little bit of gas law as well to solve this. The first thing we should do is write out the balanced equation. Glucose is C6H12O6 plus oxygen, and it'll be 6 of them, makes 6 carbon dioxides and 6 waters. Now, start with the 5.60 grams of glucose. I'm going to first convert it into moles. 1 mole, the mass of glucose, is 180.18. Secondly, I'm going to now convert it from moles of glucose into moles of carbon dioxide. There's 6 CO2 for every 1 glucose. If I do that, it will get me moles of carbon dioxide, because once again, grams will cancel out, glucose will cancel out, I'm left with moles of CO2. So if I do that, I initially get 0.186 moles of CO2. Now that I have moles of CO2, I have a temperature, I have a pressure. What I can do is use PV equals nRT. And I can solve for V. So V will equal nRT divided by P. 0.186 moles, 0.0821 is my ideal gas law constant. My temperature is 273 plus 37, which is going to be 310. Divide that by the pressure of 1 atmosphere. That will give me my volume. My volume for this problem ends up being 4.75 liters. Again, make sure that the unit is liters, because the R value constant, which I didn't have space to put down here, will tell you that it's liters for that one. That is one of the last calculations we need to know. There's partial pressure, though, which is the next one that we have to be aware of. Partial pressure was an idea came up with by John Dalton. John Dalton said the total pressure of a mixture of gases is the sum of the pressure of each gas, as if it were to exert it alone. Simple way to express this is P total equals P1 plus P2 plus da-da-da, however many pressures there are. Now this is where in class we use the udiometers to figure this out. For my knowledge, udiometer problems are not on the AP test. Instead, what you need to be able to do is what's called mole fraction. Mole fraction is represented by a capital X with the I then, where it'd be the moles, which is N, lowercase n is moles. So it'd be the moles of whatever you're intending to look at divided by the total number of moles. If we want to find the pressure of an individual gas, we take the mole fraction of that individual gas and multiply it by the total pressure. Here's the question that we're going to answer then. says what is the partial pressure of each gas in a mixture of 8.24 moles of methane, 0.421 moles of ethane, and 0.116 moles of propane at 1.37 atmospheres. The 1.37 atmospheres is our total pressure. So if I want to find the P1 or the PI, the individual pressure of each gas, I'm going to find the mole fraction of each one. To find the mole fraction, you need to find your total number of moles. So I'm going to add 8.24, 0.421, and 0.116. Once I have my total number of moles, I can take each one divided by the total and multiply it by the total pressure. So I'll show you that on the board here. First off, when I add up all those three pressures, my total number of moles equals 8.777. So there's my total number of moles. So my next thing I would do is I would look at my first gas, the methane. If I take 8.24 divided by 8.777, that will give me my mole fraction. In this case, the mole fraction for that is 0.939. Now that I have the mole fraction, I would multiply that by the 1.37 atmospheres. This will tell me the pressure of the methane, which for this one would be 1.29 atmospheres. Instead of writing down the other two, I'll just quickly talk you through it, that for the ethane, I would take, instead of 8.24, I would take 0.421. When I take 0.421 divided by the 8.777, that would give me a mole fraction of 0.0480. If I take that multiplied by the 1.37 atmospheres, the partial pressure due to ethane would be 0.0658 atmospheres. And lastly, if I wanted to find the propane's mole fraction, I would take 0.116 divided by the 8.777. That would give me a number here, multiplied by 1.37 atmospheres, and I'd end up with 0.0181 atmospheres for my partial pressure there. Again, a simple way to check and make sure does that make sense is do all the partial pressures, add up to the total of 1.37. Next is the kinetic molecular theory of gases. This is just a generalization of gas behavior. We'll learn in a little bit that gases don't behave ideally all the time, but in general they behave close to ideal. First off, gas molecules are so far from one another that their own volume is considered negligible. So once again, that idea that every gas behaves the same, like Avogadro said, kind of holds true, even though some gas molecules are much larger than others, because the space that the molecules occupy overall is so much greater than their own volume. Secondly, gases are constantly in motion, and collisions with one another are perfectly elastic. So in other words, when two gas molecules hit each other, they bounce off perfectly. They're not held together at all. There's no attractive forces there. Next, gas molecules do not attract or repel each other. Again, it's not completely true, but at the speeds that they're moving, it is pretty true. We talk about how these can be exceptions at high pressures and low temperatures, because at high pressures, gas molecules are close together, more likely to attract each other. At low temperatures, gas molecules are moving slower, so once again, they're more likely to attract or repel each other. And then the last part on this slide is that the kinetic energy is proportional to the temperature, and any two gases will have the same kinetic energy at the same temperature. So in other words, again, when you increase the temperature of a gas, they move faster, and that leads to increased pressure then as well that the gas can exert. Root mean squared is a calculation that we didn't really cover, and I'm uncertain if you need to know as well, but I'm going to go over it really quickly here. That U with an RMS stands for the average molecular speed. And to find the average molecular speed, it's the square root of 3RT divided by, that M is our capital M for molar mass. Now, in this value, the R is an energy, 8.314 joules per mole Kelvin. So this is a little bit different. Once again, the M is for molar mass, which in this case would be kilograms per mole to allow for unit cancellation. And the last thing to mention is speed. In this case is measured in meters per second for the gas. Again, I'm uncertain if you will see this or not. I just wanted to quickly bring up this equation to you. One equation that I think you'll more likely see is dealing with what's referred to as diffusion and effusion. R1 over R2 equals the square root of M2 over M1. So rate of the one gas versus rate of a second, the molar mass of the second gas versus the molar mass of the first, is one way you might see this equation. The second way is actually flipping it. where T1, the time for a gas to travel, over T2 equals the square root of molar mass of 1 over molar mass of 2. So there's two different ways you could see it. Again, if we say one is this many times faster than the other, that's referring to a rate. If we refer to it takes this gas 25 seconds to effuse and another gas 45 seconds to effuse, that's the time. And again, diffusion is the mixing of gas molecules with one another. Effusion, on the other hand, is gases escaping from one compartment to another through a small opening. Here's the problem that we're going to solve. It says it takes 192 seconds for an unknown gas to effuse at 84 seconds, and 84 seconds for nitrogen to do the same. What is the molar mass of the unknown gas? Seconds and seconds are involved, so I'm going to use this equation. So once again, I'll write it over here to begin with. Time 1 over time 2 equals the square root of the molar mass of 1 over the molar mass of 2. Once again, if this was a rate problem, these two would be switched around, so then the 2's would be across from one another, not in this case. So figure out which one you want to designate as 1 and 2. I'm going to say 192 seconds is my T1 over T2 of 84 seconds equals square root of the molar mass of 1, which is the gas we're trying to figure out. We don't know that one. Divided by the mass of nitrogen. Nitrogen is a diatomic gas, 28.02. How I would solve this is I'd square both sides. By squaring both sides, I cancel out the square root here, and then 192 divided by 84 will get me that next step there. From that point, I can multiply both sides by 28.02 to get my final answer of 146 grams per mole. If you think about it, the molar mass of this gas is larger than that of nitrogen. Nitrogen was able to effuse at a much faster pace than the larger gas. Bigger molecules do move slower, so these numbers should make sense. And that's a simple way to check your final answer when you solve for this, because it's easy to flip these around by accident, but if you realize a small gas should cover ground faster than a larger gas does, then you should be okay, but make sure you check that to make sure. The very last thing, and we're not going to actually do a calculation for this, is the non-ideal gas law. It's referred to as the van der Waals equation. Now you'll notice that it's PV equals nRT, but then there's this other stuff on there as well. Once again, N is moles, but the A and the B are known as van der Waals constants. Those would have to be given to you. In our book, they were on page 213, but for each gas, they're given a different van der Waals constant. So you could solve this equation as well. I'm uncertain if you're going to be asked to do that. They would have to give you this equation in order to solve for it. But again, this would be the last thing to know in this gas unit chapter. That's it.